Alright, we're back in Chapter 8, Section 3, talking about graphing complex numbers. Now, whereas graphing the polar equations is something new, if you have come up through trig the previous semester, this is going to be familiar to you. This is something that we do in our trigonometry class, talking about adding, subtracting, multiplying, and dividing our complex numbers on a complex plane. De Moivre's theorem, where we raise complex numbers to a power. So first of all, our complex plane. Our complex plane looks exactly like our xy real number plane. We just rename our axes. Instead of just the x and y axis, we have the real axis and the imaginary axis. So we can represent a number z, a complex number z, which is x plus or minus yi, geometrically as the point xy, where x is the real coordinate and y represents our imaginary coordinate. So that the x-axis is the real axis and the y-axis is our imaginary axis. Okay, and then it encourages us to practice. So let's draw our own complex plane, and we're going to plot the point that corresponds to the complex number z equals 3 minus 2i. Well, the real portion is going to be 3, and the imaginary portion is negative 2, so we're in quadrant 4. So I count 3 positive on the real axis and 8 down to a negative 2 on the imaginary axis, and that's where my point falls. Let's just label this point P. Now, a polar representation of the complex number can be written by finding the angle theta and the radius of the circle drawn to that point, because remember, our polar coordinates would be r theta. So if I were interested in finding the polar coordinates for point P, I'd think, okay, well, here's my angle theta, right? And then this value, however far out we are from the pole, is my value for r, for my polar coordinates. The radius, that distance from the pole to the point, is called the magnitude, or the modulus. And it's represented as what looks like the absolute value bars around z. So the modulus of our point is bar z. Use what is known about finding angles from an initial side to a terminal side and right triangles and their hypotenuse to find theta and the magnitude, or the modulus. Okay, well, that modulus of z is going to be equal to the same way we would find r, right? And r is going to be the square root of x squared plus y squared. So in this case, we have 3 squared plus a negative 2 squared, which is the square root of 13. Now, modulus is always positive because it is that distance from the center, from the pole. How do we find theta? Well, we find theta using tangent theta equals y over x, because that's what we know. We know y and x. Well, y was a negative 2 and x is 3. So when we have tangent theta is equal to a negative 2/3, I can take the inverse. So I find tangent inverse of a negative 2/3. Inverse tangent is restricted to quadrants 4 and 1, but we're in quadrant 4, so we're fine. We don't have to think about rotating our angle. When you input that into your calculator, you should come out with about a negative 33.7 degrees. If you wanted the positive value, so the negative 33.7 is that clockwise rotation from the x-axis, from the pole. If we want this rotation, we would find the difference between that and 360 and record it as 326.3 degrees. So there is r, my modulus, absolute value z, and theta. The polar location, therefore, for this point, P, would be square root 13, 326.3 degrees, or square root 13, negative 33.7 degrees. Okay, let's look at the next page. in general, we can define, let's do some definitions for our modulus. Let z equal x plus yi, that's a complex number. The magnitude or modulus, two terms for the same thing, magnitude or modulus of z, denoted absolute value z, is defined as the distance from the origin to the point xy. So we can find it by doing x squared plus y squared, square root of that sum, or we can define it as, another way our book defines it, is z times z bar. Now, I misstated this as z bar earlier. This is z bar. Okay, where does this come from? Well, z bar is the same thing as conjugate of z. My conjugates would be z is x plus yi, and then z bar would be x minus yi. And if I multiply z times its conjugate, x plus yi times x minus yi, what I'm left with, because those outside and inside products multiply to 0, I'm so sorry I had you off the screen again. So my x bar means the conjugate of z. Here's z, here's its conjugate. All I do is change the sign, the algebraic sign. If I multiply those two things together, I'm multiplying these two complex numbers. My outside and inside products add to 0, so I'm left with x squared plus y squared, because this would be a negative y squared I squared, and I squared is negative 1. So this is just another way to write the equation for my magnitude. Alright, how to convert a complex number between rectangular form and polar form. This is just a little bit of review in that x is r cosine theta and y is defined as r sine theta. Remember that we get that from the fact that cosine theta is x over r and sine theta is y over r. And using substitution, z equals x plus yi is going to be the same thing as, if I substitute in for x, I would substitute in r cosine theta. And if I substitute in for y, I would substitute in r sine theta, and then that's going to be times I right there. So I can write that, if I pull out that common factor, as r times cosine theta plus I sine theta, where my modulus is r. Now this book does not, I don't think that this book calls the shorthand cosine theta plus I sine theta. Our trig book that we've been using rewrites that as r cis theta, cosine I sine theta. You see the shorthand in there. Okay, write an expression for z equals 3 minus 3 square root 3i. First, we're going to plot the point to determine which quadrant we are in, and then we're going to find r and theta so that we can write it in polar form. Well, if I plot the point, I have my real part is a positive 3, my imaginary part is a negative 3 square roots of 3, so that's going to be a little bit further down than it is out. So my point's going to be down here. That's going to be my angle theta, and then there is that right triangle I'm looking at, where x is 3 and y is a negative 3 square root 3, and we don't know our modulus, which is r, or that absolute value bars around z. Okay, so we're in quadrant 4, and r here is going to be 3 squared plus negative 3 square root 3 squared. Now let's think about what this looks like. Negative 3, or 3 squared is just 9, but what about negative 3 square root 3? Well, negative 3 squared is 9, square root 3 squared is 3, and 9 times 3 is 27. So that's the square root of 36, which is just 6, and r is always positive. What about theta? Well, we use tangent theta, where tangent is y over x, so negative 3 square root 3 over 3 gives me a negative square root 3. That's the value of tangent at angle theta. That's one of my special angle values. So I can find the angle in quadrant 4 that has this tangent function value, and I discovered that my angle I'm interested in is 5 pi thirds. When I use r and this angle to write my solution in polar form, I have z equals 6 times cosine 5 pi thirds plus I sine 5 pi thirds. Or if I want to put it in shorthand, 6 CIS 5 pi thirds. And those are two ways to write the exact same thing. Okay, plot a point in the complex plane, convert from polar to rectangular. So we are given polar form, CIS theta form. We want to plot it and write an expression in rectangular form. Well, what do we know? We know r is -3 right there, and we know theta is 60 degrees. So let's use that to plot on our polar coordinate system where we rotate around the pole. So first we draw in our angle 60 degrees, there's theta, but then we need to move to -3. Well, -3 is going to be this direction, right? So there's our point. Now we convert to rectangular form. We know that we're going to end up in quadrant 3, so x and y are both going to be negative. So we have x equals r cosine theta and y equals r sine theta. R is -3, theta is 60 degrees. The cosine at 60 degrees is 1/2, and the sine at 60 degrees is square root 3 over 2. So my coordinates for this point, my rectangular coordinates, this is the polar coordinate. My rectangular coordinate for this point is a -3/2, -3 square root 3 over 2. They're both negative. We're in our correct quadrant. Okay, let's look at the next page. How do we multiply and divide complex numbers in polar form? Well, we can use some indifference formulas to get there, but we're not going to right now. This is kind of an aside. If you wanted to derive those formulas, that's how you would do it. We're just going to kind of give them to you. So let's say that our first complex number is just z1, and our second complex number is z2. So that z1 is using r sub 1, theta sub 1. z2 uses r sub 2, theta sub 2. Makes sense, right? If I want to multiply these two numbers together, I'm going to multiply the moduli, so r sub 1 times r sub 2, and then I'm going to add the angles. So I add theta 1 and theta 2. Cosine I sine theta 1 plus theta 2. Sorry, that subscript should have been smaller. Now, as long as the second number isn't 0, I can do division as well. When I'm multiplying, multiplication pairs with addition, right? So if I'm multiplying two complex numbers, I multiply the moduli and I add the angles. If I'm dividing, division pairs with subtraction. In this case, I would divide the moduli and I'm going to subtract my angles. Make sure you do it in order so that the first angle minus the second angle so that you get the correct result. All right, let's practice this. For the first one, well, we're given two complex numbers z and w in polar form, and we want to find the answers and just leave the answers in polar form. We're not being asked to switch to rectangular form. We're going to first multiply the two together, and then we're going to divide z divided by w. When I multiply the two together, remember I'm going to multiply the moduli, so that would be 8 times 2. And then I add the angles. So I have cosine of 40 degrees plus 20 degrees plus I sine of 40 degrees plus 20 degrees. Well, 8 times 2 is 16, and then 40 and 20 is 60. So I have cosine of 60 degrees plus I sine of 60 degrees. Don't forget your parentheses. And if I wanted to use my shorthand, I could just say 16 CIS 60 degrees. Either answer is perfectly acceptable. What about division? Well, when I'm dividing, I divide the moduli, and then I subtract theta. Alright, so 8 divided by 2 is 4. And then I'm going to have cosine of 20 plus I sine of 20 degrees in parentheses, or 4 CIS 20 degrees. Okay, so that's how we multiply and divide with complex imaginary numbers. What about raising them to a power? Well, raising a complex number, raising any number to a power is just repeatedly multiplying it times itself, right? We could do that, but keep in mind that each complex number is basically a binomial. So we would be squaring it, cubing it to the 4th, all by hand, and that gets really lengthy. So let's see if we can find a shortcut for that. Let z equal this general term of my complex number in polar form. If I want to find z squared, I'm just going to do z times z. So using my theorem, my property for multiplication, this would be r times r would be r squared, and then I would have theta plus theta is 2 theta. So cosine 2 theta plus I sine of 2 theta. Now what if I, whoops, sorry guys, what if I wanted to do z cubed? Well, z cubed is just z squared times z. So I would say, okay, that takes this result, r squared times cosine 2 theta plus I sine 2 theta, times my original z, r cosine theta, I sine theta. Now I multiply these two together. When I multiply these two together, I get r squared times r is r cubed, and then I'm going to add the angles, so that becomes cosine of 3 theta plus I sine of 3 theta. Okay, now what about z to the 4th? Well, I could either do z cubed times z, or I could do z squared times z squared. Either way I want to do it. Let's think about doing it z cubed times z. Well, r cubed times r is going to be r to the 4th. And then I'm going to add the angles, so that is going to be CIS 4 theta, right? Do you start to see a pattern here? When I did z squared, I got r squared and 2 theta. When I did z cubed, I got r cubed and 3 theta. I did z to the 4th, I got r to the 4th and 4 theta. That's my pattern for de Moivre's theorem, which is how I raise a complex number to a power. When I am raising a complex number to the nth power, I raise the modulus to that power, and then I multiply theta times whatever the power is. As long as my exponent is a positive integer. De Moivre's theorem only applies when the power I'm using is a positive integer. Okay, now we are going to write 3 CIS 40 degrees to the 9th power in standard form. So standard form is my rectangular form. Not polar form. So we want to think about that, okay? Don't stop too soon, basically. Okay, so first we're going to apply de Moivre's theorem. So 3 to the 9th, and then I have cosine of 40 degrees times 9 minus I sine of 40 degrees times 9. Well, 3 to the 9th is 19,683. And 40 times 9 is 360, so that would be CIS 360 degrees. That's polar form. But I want standard form. So I'm going to say, okay, I had 19,683 times cosine of 360 plus I sine of 360. Well, cosine of 360 is 1. So that's 19,683 times 1 plus I times the sine of 360. Well, let's not just multiply that in yet. Let's do cosine of 360 is 1, I sine of 360 is 0. So that is I times 0, that just leaves me with 1. So 19,683 is my standard form of that complex number. Okay, let's go again. Still writing our number in standard form when we're at the end. But notice I'm starting in standard form. Well, de Moivre's doesn't work in standard form. To use de Moivre's, I have to get it in polar form. So the first thing I do is going to be to plot it on an imaginary set axes. So my real number part is 1. My imaginary part is a negative square root 3. When I sketch this, I've got a point down here at 1 negative square root 3. That's my angle theta. I'm in quadrant 4. So Z is going to be, modulus. The modulus is going to be square root of 1 squared plus a negative square root 3 squared. Well, 1 squared is 1, and then 3, so square root 4, that's easy. So that modulus Z bar or R is 2. Now I need to figure out theta. Tangent theta is y over x. In this case, y is negative square root 3 over 1. So I've got an angle in quadrant 4 whose tangent function value is the negative square root 3. We've already worked with that. That was 5 pi thirds. I know r and theta, so I know the polar form so that I can use de Moivre's theorem. Now, I have not been given instruction as to whether I need to work with this in degrees or in radians. It doesn't make any difference. If I want to put it into degrees, what is 5 pi thirds in degrees? Well, that would be 300 degrees, right? Because I'm 60 degrees away from a full rotation. So I would have 2 CIS 5 pi thirds, or I would have 2 CIS 300 degrees, whichever form is the most useful to me, whichever one I want. But this is my polar form, and I can use it to use de Moivre's theorem. Okay, so de Moivre's theorem says I want now to raise it to the 10th power. So I raise my r to the 10th power, and then I multiply times 10 in here. So no matter which one I'm working with, I'm going to have CIS, well, this would be 50 pi thirds, or 2 to the 10th, CIS 300 times 10 would be 3,000 degrees. 2 to the 10th, when I plug that into my calculator, is 1,024. I need to simplify this a little bit, right? Because I need to get it back in standard form. So if let's just go with one of these or the other. We need to figure out the smallest angle that this is going to be coterminal with. If we do, you know what's going to be easier for me, I think, to work here. If I do full rotations, that's going to be 6 pi thirds is one full rotation. That would be 2 pi. So how many 6's go into 50? Well, 6 times 8 is 48. So 8 full rotations would get me to 48 pi thirds. 8 full rotations would get me to 48 pi thirds, which leaves 2 pi thirds over to be coterminal. So this is 50 pi thirds is coterminal with 2 pi thirds. 50 pi thirds is coterminal with 2 pi thirds. So when I'm finding, transferring my polar form to standard form, I'm going to start by saying, you know what, yes, I've got 1024 CIS 50 pi thirds, but that is going to be coterminal, so I'm going to have the same value as 1024, and I'm going to go ahead and write this out in longhand, cosine of 2 pi thirds plus I sine of 2 pi thirds. Because to get this into standard form, I need to know the actual values here. Well, 2 pi thirds has a cosine function value of -1/2. Sine of 2 pi thirds is a positive square root 3 over 2. And I distribute that inside, and I get -512 plus 512 square root 3i, or 512i square root 3, depending on where you stick that I. It offers to let me use the calculator to confirm. You guys don't need to use your calculator to confirm unless you're confirming here. If I chose to get 2 pi thirds in degrees, I could have said it's coterminal with 1024 CIS 120. That's the same thing in degree measurement instead of radian measurement. Notice it doesn't matter whether I work with it in degree or radian, but de Moivre's theorem has to be worked with in polar form. So if I need standard form, I have to start with my standard, go to polar form, and then come back to standard form at the end. Okay, our last page of our section here. In previous courses, when you were asked to solve x squared equals 4, how many answers did you get? Well, square root of 4, there are two possibilities, right? Because when we take the square root, we have x squared equals 4, and I take the square root. I said, you know what? I'm going to consider plus or minus, because a positive 2 times 2 is 4, and a negative 2 times negative 2 is also 4, because there are two values of x that when squared gives us 4 as a result. Now, this is a did you know that anytime you're taking a root, whatever root that is, the nth root, that's how many results there are going to be. I took the square root of 4 here, I got 2 results, they're both real. What if I do the cube root? There's going to be 3 results, they may just not all be real. So here is our theorem to help us find complex roots. We did raised to a power, now we're going to find the complex root. As long as, okay, so we're going to let n greater than or equal to 2 be an integer. N is going to be our nth root. So z sub k is going to be the nth root of r. So if we are taking the nth root of a complex number, we take the nth root of the modulus, and then we divide theta. Theta divided by n. Plus, and we think, okay, if I rotate it, I'm going to move that rotation around as well. I sine of theta divided by n plus 2k pi divided by n. Interesting things to know about roots. Complex roots are going to be evenly spaced. Going to be evenly spaced around the circle. They will repeat because your angles are angles of rotation. But for example, if I'm finding fourth roots, I will have 4 unique fourth roots of that number. If I'm finding cube roots, I will have 3 unique cube roots of that number. Because they are evenly spread around the circle, that means wherever my starting place is, for example, if I'm finding fourth roots, 360 divided by 4, I will have a root every 90 degrees. If I'm finding cube roots, I will have 3 unique cube roots before they start to repeat, and I will get one every 120 degrees. They will fall every 120 degrees. So once I find the first one, I add 120 to find the others. For the fourth roots, once I find the first one, I add 90, add 90. Now that shows up right here, divided by n. I take my rotation, divide it by n. If I'm finding fourth roots, I divide it by 4. They're every 90 degrees. If I were finding cube roots, I'd divide by 3. They're every 120 degrees. Let's work this one out. Find the complex fourth roots of -2 plus 2i. I know I will have 4 unique roots, and they will fall every 90 degrees. So once I know where the first one is, I know the next one will be 90 degrees on a round. 90 degrees is the same thing as pi half if I want to do radians. And I think, yeah, we're going to work this first problem in radians. Okay, so first I need to plot it and get it in polar form. -2 plus 2i, so I go -2 on the real axis, -2 on the real axis, +2 on the imaginary axis. So I'm actually up here in quadrant 2. This is -2, this is +2. There's my angle theta. R is going to be square root of 4 plus 4, because I square those and find the sum, which is the square root of 8, which is 2 square root 2. And theta, well, theta is, remember, tangent theta is y over x. So we've got -2 over -2, which is a -1. That angle is going to be 3 pi fourths, because I'm in quadrant 2. And it's my 45, my pi fourth angle in quadrant 2. So my polar coordinates are 2 square root 2, 3 pi fourth. Okay, now I find z sub k using the complex root theorem. I want to find the fourth roots of this number. Well, so I've got 2 square root 2 CIS 3 pi fourths. And I want to find the fourth roots. So where n equals 4, I'm finding the fourth roots. So I take the fourth root of 2, no, that was right, sorry, fourth root of 2 square root 2. And then I've got cosine, you know what, we're just going to do my CIS. I've got a mess there. I apologize, guys. Fourth root of 2 square root 2 CIS 3 pi fourth divided by 4 plus 2 pi k divided by 4. And that gives me how far apart the roots are, which we already know there's 4 of them. They're pi half apart. This is just pi half k. Okay, so let's go back here. 3 pi fourth divided by 4. So I've got, that's going to be 3 pi 16th. So this is CIS 3 pi 16ths plus every pi half, right? What about this? Well, you know what? Simplifying that square root 8 didn't help me here. What if I just rewrote this as the fourth root of the square root of 8? Well, that is the same thing as taking the square root of 8 to the 1/4 power, which is 8 to the 1/8. So I need the 8th root of 8. So I have the 8th root of 8 CIS 3 pi 16th plus square pi half k. So to find my fourth roots, my first one is going to be here. And my next one is going to be here plus pi half. And then the third one will be plus another pi half. And then the fourth one will be plus another pi half. Well, what is pi half in the terms of 16ths? Pi half in the terms of 16th, pi half is going to be 8 pi 16ths. So that's what I'm adding every time, 8 pi 16ths. So for my first root, I have 8th root of 8 CIS 3 pi 16. And then I add 8 here. So the next root is going to be, so that's z sub 0, the first root. The next root is going to be 8th root of 8 CIS, and I add that 8 pi 16th, I get to 11 pi 16th. Then z sub 2, the third root, is 8th root of 8 CIS plus another 8 gets me to 19 pi 16ths. And my fourth root, z sub 0, z sub 1, z sub 2, z sub 3, is going to be rotated another pi half So I have the 8th root of 8 CIS 27 pi 16ths. 27 pi 16ths. So those are my 4 roots. And they were equally spaced. If I wanted to graph those, it doesn't ask me to, but if I wanted to graph those, I would think about where this first one would be. Now, this 8th root of 8 is going to be how far out I go, right? It's going to be that R value. Well, my first root, 3 pi 16ths, is almost, see, 4 pi 16ths would be a pi 4th, so it's almost pi 4th. So it's going to be about right there, and then I add 90, and then I add 90, so what I'm going to end up with is this. I'm going to add up with roots all the way around my circle. So 8th root of 8, CIS 3 pi 16th, 8th root 8, CIS 11 pi 16th, because 8 pi 16th would be pi half. And then I've got 19 pi 16ths down here, 8th root of 8, CIS, and then I've got 8th root of 8, CIS 27 pi 16ths. So that's where my roots fall. You can confirm that these answers are correct by entering each of your results into a graphing calculator or any calculator and raising it to the 4th power. The result on each should be -2 plus 2i, because that's what we started with. If I take this value and raise it to the 4th power, put it in parentheses to the 4th power, I should get what I started with. Alright. Each of your results in the 4th... Oh, we did ask to do that, and that's E, right here. When graphed, they lie the same distance from the origin, or on the same circle. If you plot the angles, you notice that they are all 90 degrees, or pi half apart, and they are 8th root of 8 out. Alright.